If you shine a single flashlight in a pitch-black room, it looks incredibly bright. Shine a second one and the room gets brighter. But does it look twice as bright? Not even close. To double the perceived brightness, you actually need 4 flashlights. To triple it, you need 8. Our eyes do not perceive the world linearly. We perceive it logarithmically. The same thing happens with your hearing. The difference between a whisper and a normal conversation feels similar to the difference between a conversation and a shout, even though the physical energy of the sound is thousands of times greater. Our senses are built to compress the universe so we can survive in it. But when we are taught this in school, we are handed a scary looking button on a calculator labeled log and told to memorize rules like log base b of x. It feels completely arbitrary. Today, we are going to throw away the calculator and see what a logarithm actually is. We will build it from scratch using nothing but a single diagonal mirror. Before we can understand the mirror, we need to look at what it is reflecting, the exponential world. Imagine a quantity that starts at 1 and doubles at every step. Step 0 is 1. Step 1 is 2. Step 2 is 4. Step 3 is 8. Step 4 is 16. The math is simple. Every step right, we multiply by 2. This is 2 to the x. The input is the number of steps, and the output is the final size. It is a forward machine. You feed in a step, and it spits out a value. If you plot these points and connect them, you get a curve that starts slow, then shoots straight up to infinity. This is exponential growth. But what if we run this machine in reverse? What if we start with the output and ask for the input? Instead of asking, where are we after 3 steps? We ask, how many steps did it take to reach 8? We trace back from 8 on the vertical axis, hit the curve, and drop down to 3. Simple. What if we want to reach 7? It is somewhere between 2 and 3 steps. But how do we write this question mathematically? That is the logarithm. The logarithm is not some mystical operation. It is literally just asking the reverse question. How many multiplicative steps does it take to reach this size? If 2 to the x equals y, then the number of steps x is log base 2 of y. To see this reverse machine visually, we draw the diagonal line y equals x. Now, we reflect the entire exponential curve across this line. In a reflection, every point swaps its coordinates. 3, 8 becomes 8, 3. 2, 4 becomes 4, 2. 0, 1 becomes 1, 0. The horizontal axis of steps and the vertical axis of size trade places. The resulting curve is the logarithm. It grows incredibly slowly, compressing the horizontal axis just like our eyes and ears compress light and sound. That diagonal line is the mirror, and the log is just the reflected twin of the exponential. This mirror has a superpower. It converts multiplication into addition. Why did John Napier spend 20 years calculating log tables 400 years ago? Because astronomers of his time had to multiply massive numbers by hand, taking days. Napier realized that if you add the logarithmic steps of 2 numbers, you get the logarithmic steps of their product. Log of a times b is log a plus log b. By mapping numbers to this mirror world, Napier turned hard multiplication into simple addition. He literally saved years of astronomers' lives. And the base changes everything. Base 2 counts doublings. Base 10 counts how many times you multiply by 10, which is just counting zeros. Log base 10 of 1,000 is 3 because 1,000 has 3 zeros. Base e is nature's natural log, but no matter what base you slide to, they are always perfect mirror twins across that diagonal. Next time you see a log, don't think of a button on a calculator. Think of the mirror. Which math concept should we mirror next? Let me